Here we're going to return to yet another familiar example, and that is our pendulum, where we have a particle P that is attached to a rigid rod, and that rigid rod can rotate about point O. So I'm going to start by, again, just writing out our reference frames, A1 and A2 for frame A, and then for frame B, we have B1 and B2, and then the angle between them is theta. And this rod has a length of L. So let's draw the free body diagram for P. So we have a gravitational force that's acting on P, and then we have a tension force T. Now, again, we have a gravitational force is a conservative force. However, tension is non-conservative. However, there is no movement or no displacement in the direction of tension. So again, if I draw this here, right, this is our tension here, there's no movement of the particle in this B1 direction, right? I mean, you could even think of it as if I were to take the derivative, so if I were in the B frame of LB1, this is equal to 0, right? And so because there is no movement in that direction, that means that this non-conservative force T does no work. And so the only force that does work is mg, this gravitational force. And so that allows us to use the conservation of mechanical energy method. And so to do that, we use the equation that kinetic energy plus potential energy is equal to some constant, which I call here C. So we'll start by calculating our kinetic energy, which is 1/2 m and then v squared. So this becomes, so first, sorry, we should calculate our position vector, of course. So as I wrote up here, that's actually equal to LB1. And then our velocity, now this is in the A direction, or in the A frame, so we can use our magic formula, which says that our velocity is equal to 0 times theta dot B3 crossed with LB1. And so that gives us L theta dot B2, so we can plug that in up here. So we have 1/2 m, and we have L theta dot B2 squared, which then becomes 1/2 m L squared theta dot squared. So next, we need to calculate the potential energy, which is equal to mg y, and this y, right, is equal to the distance between, so it's the vertical distance between, in this case, our reference position, which has 0 potential energy, which we're going to call our reference position the hanging position, so when the theta equals 0. So in which case here, that is, right, so the position of this particle with respect to O in the vertical direction here in the A1 direction is L. And so to get ultimately what we want, oh, I drew this picture terribly. Just draw it one more time. There we go. So this is L, this is where our potential energy is equal to 0. So what we need is this height here, y. And so we can calculate by doing the following. Let's project this point P over here, so that should be just a straight line. And we can calculate, we know that this here is equal to L cosine theta, right? If theta is here. So this y term here, we can write that y is equal to L minus L cosine theta. So we can plug that in now to our equation. So we get potential energy is equal to mg. We can pop the L out here and write 1 cosine theta. Now we simply take the sum. So we have kinetic energy plus potential energy is equal to a constant. So we write 1/2 ml squared theta dot squared plus mgl 1 minus cosine theta equals a constant. When you take the derivative of both sides, we get ml, so squared theta dot squared plus mgl 1 minus cosine theta, and this is going to equal 0. So if we take this derivative, this ends up becoming ml theta dot theta double dot plus, and so here, if you were to distribute this, turns out that mgl by itself is going to go to 0. And so we only need to take the derivative of negative mgl cosine theta. And so we have mgl theta dot, this is sine theta, right? And so because we have a cosine, theta is negative, but then it's multiplied by negative, so we get a positive there. This is equal to 0. And so we can cancel out some terms. We can get rid of an m. Oops, this should be a squared, so we can get rid of that L, and we can get rid of that theta dot. And so what we're left with is L theta double dot plus G sine theta equals 0. And so this here is our equation of motion.